We'll list these as properties of an isolated electrostatic conductor. That's I'm sorry, an isolated conductor that's in electrostatic equilibrium. Now the idea of a conductor in equilibrium, we saw before when we charged conductors in by conduction and induction. The concept of equilibrium exists when we have basically no currents on the conductor. And we will only have currents if we have external fields affecting them and the forces associated with the effective field. So basically by saying electrostatic equilibrium, we've got three basic properties which are all related. There's no currents on the surface or inside, no external fields, no fields in or outside, and no forces affecting them at all. No external forces. So we'll say that and then make some qualitative, they're not proofs, but justifications as to why that is the case. So electric field then is zero, both inside and on the surface. So this reads as the electric field is inside and electric field is zero inside and on the surface of an isolated electrostatic conductor in equilibrium. The argument follows as such. Basically, it's a simple argument. We know by definition that E is defined as F over some test charge or charge. So if there were electrostatic fields that would be allowed inside a conductor, that means that those fields, now these are external fields or net fields, even for, just any field, then there would be forces associated with those fields. And the free charge in the conductor on the inside would see those forces as an external force, right? And therefore, you would have collective movement of charge, and that would be current on the inside. So because it's isolated, there are no currents, then that would violate the whole point of it being isolated. Yeah. So then no current on the inside. Now, when it comes to conductor, I've talked about this before, that there really is no difference between the inside and the outside. I know that seems a little bit weird, but if you think about the Einstein model, when we break it down and look at it from the point of view of the atomic lattice, there's no distinction between the atoms on the outside or the surface of the lattice than those on the inside. So the idea is you can make a statement that you can get, if you're on the inside, you can get infinitesimally close to the border on wherever that may be. And that border just becomes the atoms that are the last atoms in the lattice, which are just the surface of the material. So if you were to move along, nothing changes in terms of the consistency of the material. So, the lattice just stops. So if you're infinitesimally close to the surface and there is no change from, along that region of space that you're traveling, and there are no currents on the inside, then there are going to be no currents on the surface. Again, it's a qualitative argument, but that's the argument that's kind of made at this level outside of any more advanced type of proofs. Yeah, that's it. So that's one property. Second property, again, we've already talked about, but from the point of view of field, but we'll say it again. All excess charge lies on the surface of a conductor. So when you charge by conduction, induction, whatever, that charge will be found on the surface, not on the inside of the conductor, but always on the outside, on the surface of the conductor. Now, in that case, we're not, obviously it is from internally, because of things we've talked about before, but we even talk about like when you take the object and make it into something like, for example, a hollow conductor. So even in that case, we're not just talking about in between the walls of the conductor. We're talking about if you have a closed surface, like in the case of, this was initially proved by Michael Faraday when he took like a farmer's pail. It's called the ice pail experiment, like like a tin pail or aluminum pail that you use to put ice in or carry milk in or something, like big farmers or something. So that's kind of, it's a pail, right? It's a bucket. So it's got, there's inside the walls of the metal, but there's also inside and outside of the bucket. So in this case, we're talking about both really, but in Faraday's case, he was really talking about if you form a metal object into a closed surface, then even in that case, the charge will be found on the outside of the surface, not on the inside, always. And basically for the same reasons. You can kind of say that my argument is very simple, that if you have charge, if you could put charge on the inside of the object or on the inside surface formed by the object, either way, the charge would try to get as far away from other charges, the excess charge, as is possible. And so therefore, ultimately, just based on geometry, the farthest place apart would have to be the outside surface of the material. And again, the idea is not that you have current running around the surface to get far away, because then it would violate the first principle that there would be currents moving inside or on the surface or whatever. It doesn't happen like that. It happens like the Borg from the original Star Trek, where once charge is on the metal, all the free charge communicates. And so some excess charge, some free charge, someplace in the equilibrium position or near the equilibrium position would just pop up to the surface and take that position, and the excess charge, wherever it's placed, just becomes embedded within the material and becomes free charge. So that happens all over the surface simultaneously as the excess charge becomes incorporated within the body of the free charge. So therefore, you could then have this equilibrium status of the excess charge achieved without any current, any collective charge moving or charge moving over the surface in any way or inside. So We say that excess charge resides on the surface of a conductor. All excess charge. Okay. With that in mind, I've told you about the Faraday ice field experiment, but you could probably find some qualitative examples. I don't know if your book specifically goes through, but I would probably Google it and just read through maybe some of the historical context and also just how he did that. I might put a note here. Uh, it's one of the famous experiments in physics. And is the experiment that proved this idea. So we gotta take a look at that. And I think he probably did this in the 1820s, maybe 1820s or 1830s, somewhere around there. The electric field, any external electric field must be perpendicular to the surface. Now we've said that as a property of, we talked about that back when we looked at electric field lines, but I don't think I justified why. And here we can do so, we'll do so now. So E, external, or even, it doesn't even the charge associated with, the field associated with the charge itself. And this again is for an isolated conductor. So I guess if it's isolated, that means that it wouldn't be an external field. It would be a field associated with the excess charge on the conductor. That's right. Yeah. So E is always perpendicular to the surface. Now, first, this is the electric field associated with the excess charge. Um, this is also somewhat just based on common sense, I guess, or kind of a deduction of, well, common sense, rather an application of these last two principles. So let's take a look at what would happen if the field were parallel. If we had a field that was at some angle other than zero, other than 90 degrees to the surface. So say we have some charge here. So let's say this is the surface of the conductor here. This is a conductor. And this is like the inside of the conductor, I guess. So maybe we've got some positive excess charge on the surface here. So positive excess charge. So if we have positive excess charge, let's assume that the field is is not perpendicular. So this charge has a field. Now we can make it something that would have to be in the same direction. So you can do that better. Somehow, just even writing that like that looks a little weird because kind of take that for granted. I've just told you that charge points from, well, I guess it doesn't look weird if there were, you have to see if there was some sort of, well, actually it does look weird. Anyway, so let's say that it was like that. The E field was like that. So proposing. So if we take one end, they all should be the same length, I guess. So okay. So I'm going to put an E and a question mark just so you don't. So if that's the case, we would both have an electric field. Let's just do this one right here. I need some more space. So we would have two components, a perpendicular component. So E perpendicular here, and then E parallel here. So you would then have an electric field parallel to the surface. So E parallel. Now, if that's the case, look at this. You've got positive charge, that's excess charge along the surface, right? But then you also have some collective field that's parallel to the surface. So this is the free charge. Which means that you would ultimately have surface currents moving around, because they would feel the force. It's back to this argument that if there's an electric field present, then there must be a force associated with that electric field. And that force is on, charge, any charge in that vicinity. So if you had surface currents, then it basically violates all these properties we just said. It violates the idea that it would be if it's in equilibrium and isolated, there will be no currents just from the definition of the thing. But then just going back and look at all these implications of these other properties, they would all be violated. And so we practically don't see that whenever we charge it. You don't just arbitrarily have currents running around on some conductor when you charge it. So that's not true. So that must mean there are no parallel components of the electric field to the surface, which means the only components are perpendicular, which means the field itself it's just perpendicular. So that's the argument that's made. And so only electric fields are only perpendicular to the surface for an isolated conductor. Yeah. And finally, we'll say that charge accumulates, if you have a conductor that is not uniform, then you find that charge accumulates in the corners or the sharp areas. Again, this is also an artifact of the property of charge, that it basically tries to move away from, itself, like charge repels. And so it moves as far away as possible, like given the geometry of the object, that's always going to be on the outside. But even on the outside, it kind of accumulates in places that I guess we would call corners if the geometry of the object is not uniform. So I have been using uniform objects, like we did Gauss's law with spheres and cylinders and things like that. So if you just think about a sphere here, if you charge a sphere, the reason that it's uniform, the charge will excess charge will redistribute itself uniformly, is because there are no corners. So it just moves around on the outside surface, every place equally distributed. Okay, so it really is that's a kind of a property of the geometry of the object. But if you did have objects that were non-uniform, like something like just consider an oval shape, what you would see is that it won't be equal. The charge won't be evenly distributed over the object as it moves away. It's going to kind of be more accumulated on the areas where you have the corners. And when I say accumulation, I'm talking about the space between the charge. So here on these corners, it'll start to look maybe something like that, where the surface area, the charge per unit area, becomes higher, just because the accumulation is just naturally the way it occurs because of the Coulomb force. So basically, we say that charge accumulates at corners and sharp edges for objects. Yeah, cool. Of non-uniform objects. All right, and that's that. Oh, actually, no, we got a couple of things. So that's most of that we had said before, or kind of said. I didn't give the justifications. I just kind of said it. But a couple other things here about potential that's associated with this. So we know that we said E is zero everywhere inside or outside. So you could look at that a couple ways. Let's just keep this going then. So properties, let's do it here. So there's a relationship between E and L, E and V. We now have this relationship that basically delta V is equal to negative integral E dot dl. So there's a couple places you can get this, E dot dr or E dot dl, whatever. I'll put E dot dr. But this is one. Now the delta V, that's the potential. That's V final minus V initial anywhere, whatever, either around the conductor or on this associated with the conductor inside, outside. Now remember, this is a scalar quantity, not a vector. But if E is 0 inside and outside, or just everywhere, then that whole integral is 0. So basically you have that delta V is equal to 0 for the conductor. So delta V equals 0. But what is that saying? It's saying that V. So let's say that I were inside the conductor. That's how I like to make the argument. If I'm inside the conductor and the E field is inside, then that means that anywhere inside the conductor doesn't mean that the potential is 0. It means that the change in potential is 0, which means that you can have a potential inside. It just can't change, right? Because delta V means that what you're saying is that, remember, potential is energy per unit charge, potential energy per unit charge. So if you move from point A to point B inside the conductor, that means that, so like, let's say that this is a conductor and I'm on the inside. So I know I can't draw it three-dimensionally, but just assume that it is. So I've got like point B or point A and point B inside the conductor. So there's a potential at this point, a potential at this point. It means that since E is always 0, if I go between those 2 points, the potential doesn't change. So what we say is that, based on this guy, that V, it doesn't matter whether you're going from, let's say I'm going from A to B. So delta VAB is going to be VA minus VB. Anyway, it equals 0. The point is that ultimately VA will equal VB. Now, the trivial thing is that the potential is 0, then obviously 0 equals 0. But the point is that it doesn't have to be. There can be a non-zero potential inside. It's just that it's not going to change. And that's a property of conductor, that delta V, the change in potential, is 0 inside a conductor, so that everywhere inside a conductor, the potential is constant. So that becomes a property. Now we could say everywhere on the surface, the potential is constant for the same argument we made over here, that you can make one of these positions infinitesimally close to the surface. So not only is basically everywhere on a conductor, the potential is constant. Inside, outside, not only is it this doesn't change, but it's also the same value. And that, I guess I kind of usually write that as two different properties. So we can say that actually I need to take a quick break. I'll be right back. Yeah. Yeah. So, because of this situation, there are several implications. Um, yeah. So, the we say that VB equals VA on the surface of a conductor. Now, VB and VA, as I said, are arbitrary points. So, we'll make this point 5 because you can be infinitesimally close. Well, actually, on the I justified it by saying on the inside first, and then said that a point on the inside can be infinitesimally close to the surface. But either way, I'll just make that first on this inside a conductor, everywhere inside. And then similarly, VB equals VA on the surface. And again, this is an isolated conductor we're talking about. A charged isolated conductor. um, and we can also say that because the potential is the same, if we have, everywhere on a conductor on a surface, if we have an excess charge and we try to move it, it doesn't require any work to do so. And you can see this from the general definition of potential energy, right? That because work is equal to the negative of the change of potential energy, right? Or if you take the absolute value of the work, equal just to the change of potential energy. But the change in potential energy is equal to 0. So that means that that guy goes to 0. So again, we're back to delta V is equal to 0, which leads to VA equals VB. But because delta V is 0 on the surface of for an isolated conductor, the work has got to be equal to 0. So it won't require, if you try to move those charges around. And that's just, we've kind of justified it because that work is equal to the integral of F dot dx, right? Oh, you know what? Sorry, I should have a Q here. Sorry about that, because that would mean that delta V and work are equal to the, oh no, yeah. Sorry, I wrote that as E, so I don't. If I wrote it as F, I would need, because E is equal to Q divided by F. So that's if I wrote that in terms of F, I would have to put a 1 over Q inside. So that's fine. So this is minus E dot D dr, and this is F dot dr. So I guess we're good. Yeah. So because E is related to F, you could kind of anticipate that or extrapolate that possibility. But point is that we have no work on the surface of a conductor. So I guess I should write that as a property, that no work is required to move excess charge. No work is required to move an object between 2 points that are at the same potential. Yeah, so to move Now, I have offered you a couple of different perspectives about this. We're saying that if you were to move excess charge between 2 points, if it were to move, then there would be no work required to do so. If you really think about the specific details of that, we're saying that there wouldn't necessarily, you would have basically things moving without any kind, or translating without any kind of force. Because if there is a force and that force causes something to translate through a distance, by the definition of work, force is equal to F times, dot dx or dot dr. So how, how does the charge then redistribute itself? And the only kind of visual that I can come up with is the one that I've told you, where it doesn't actually translate. It kind of acts like the Borg, and just one charge immediately incorporates itself, an excess charge incorporates itself into the free charge, and then everywhere over the surface of the conductor where there needs to be a charge to constitute an equal distribution, then the free charge just kind of pops up to be in those positions. So there's no need for a charge to move around, translate around in order for there to do so. And you might say, well, when a charge becomes incorporated, you place excess charge on the surface and it becomes incorporated inside the free charge, there's some infinitesimal distance that it has to translate to kind of go inside. Well, then the argument there is that, as I told you before, the inside is infinitesimally close to the outside. There is no change in the constitution of the material in order to distinguish inside from outside. So when I place an excess charge on the surface, I'm basically placing it infinitesimally close to recharge that's on the inside. So that distance that it has to move in order to be incorporated in the body of the free charge, in the sea of the Fermi sea of charge, is practically zero. It's a kind of a qualitative argument, I know, but that is the argument that's made. And it for me, it satisfies everything. I like it because, just at this level anyway, because it ties up all the loose all of the loose ends of all these points from a qualitative point of view. And also I can visualize it. I can visualize the possibility of this being the case. So for me, it satisfies everything. So yeah, that's the full argument and all the different properties. I guess I have these kind of broken down into seven different properties. Some of them focus from the point of view of the electric field, and some of them from the point of view of the electric potential. But in the end, they're all very much related. So that is the view of that rounds out our view of a conductor, incorporating the Einstein model that I started the course with all of these properties associated with, the electric field and the electrostatic potential. That is how we describe a metal. And of course, an insulator is kind of related to that from the Einstein, but it doesn't have a lot of these properties because there's no free charge associated with it. So basically, and everywhere we say, because there's no free charge on an insulator, and therefore essentially you could say that all these properties, the negative of these properties, are associated with an insulator, because charge will stay where you place it. So you can't have accumulation of charge. It's not going to be distributed evenly. You can't have fields inside and outside. You can't have excess charge, all the things that we kind of can say that are the negative of those are the properties associated with an insulator. And it all extends because there's no free charge. It all kind of, these differences occur because there are no free charges inside or associated with a non-conductor. And there are associated with a conductor. That's the major difference, at least from this kind of sophomore physics point of view. We could say that. So everything wraps up and ties up in a nice, neat box. No loose ends, quantitatively or qualitatively. So that's it. That's what I want to say there about. All right, capacitance. Well, I'll tell you up front, the purpose of a capacitor is to store charge. And in the process of storing charge, a capacitor stores energy. So by storing the energy, one can gain control over the energy and use it within a circuit, control it and use it for specific types of circuit design. And that's it. That's the simple and most concise, I guess, definition of a capacitor and what it's used for and what its purpose is. Capacitor stores charge and therefore stores energy that can be controlled and utilized in a circuit or circuit design. Store charge. Yeah, that's it. Now, the symbols, I guess we should maybe get into talk a little bit about symbols for elementary circuit design. We'll be utilizing them from this point on, these symbols. You want to know what I'm talking about. So symbols. Um, yeah. So this guy, two straight lines of equal length are together in a circuit is a capacitor. Let me do that this way. Oh, so capacitor. Its symbol is C. Now you can also see, I don't know if there's a specific name for it, but capacitors that may look like this, where you have a bar here, some look like curved bar. And what it means is that current can only run in the direction, in one direction. Well, you know what? I'm not gonna talk about that because we're not gonna be using those here at all anywhere in the book. So I guess actually, is that a diode? Yeah, I guess it's a diode. So it's a whatever. We'll just deal with this. So capacitor, resistor. Its symbol is capital R. And yeah, so the symbol is usually put right above it, so I'll do it like that, or below it in the circuit, or either that or the value of the capacitor. So yeah, and then a battery is also 2 bars, but one is short and one is longer, and they're symmetrically arranged. Sometimes you see a minus on the shorter one and a plus on the larger one. And of course, the symbol is delta V for voltage, which we've already covered what that means. A light bulb is basically just a fancy resistor. Sometimes you'll see, just to make it interesting and to kind of mimic maybe some simple experiment that's being done in the lab, because you can have small light bulbs that you can connect with, small circuits. It's something like that, kind of a squiggle on a circle. And usually there's the main property that we associate with the light bulb is resistance. So even though it is a light bulb, you'll see usually a resistance associated with it. Ultimately, we will talk about inductance as well. And an inductor is a coil of wires that's kind of coiled, and so is a resistor, really, but it's basically something that creates a stronger magnetic field. We'll talk about magnetic fields associated with current wires. And the symbol for an inductor is basically a coil, which it kind of matters what direction it's coiled in. And the symbol for an inductor is, oh my gosh, wow, just not I, it's, oh gosh, inductance. What is the symbol for inductance? I'm drawing a blank. Wow. Okay. Mm. Yeah. L is what Halliday and Resnick uses, and that's generally what I use as well. So it's kind of throws you off because it's just some arbitrary symbol. We couldn't use I because I could be confused with current. So L is used for the symbol for inductance, and it doesn't have anything to do with the spelling. I think those are the major symbols that we need right now. And I guess the other thing that I threw up was a diode, but we won't need that. So I'm not going to put that up. It's yeah. So those are the symbols that we use for capacitance. And but right now, we are going to focus on how a capacitor is created. How does charge build up, accumulate on a capacitor? And I've got kind of a qualitative discussion that I like to explain to you so that it helps you to understand certain properties associated with the conductor. Now, we're going to do we're going to start now by looking at a simple circuit. Now, this circuit is an ideal circuit. What we will find next chapter is that you always need a resistor in a circuit in order for current to flow. for charge to move collectively through a wire. Now, again, going back to the Einstein model, what charge is moving collectively? It's the free charge that's inside the conductor. That's already there. And I've already described to you what a potential difference is, but let's make it a bit more practical. Basically, potential difference, a battery, right? Voltage, energy per unit charge, all the stuff we defined in the last week or so. It's, we call it creating a potential hill. When there's no battery in a circuit, so this is, say, a free charge that's inside the material. When there's no battery in a circuit, it's like sitting on a flat surface. And remember, we define it as potential energy per unit charge. In the case of gravity, we have gravitational potential energy. In the case of electricity, we have electrical potential energy. When we divide electrical potential energy by the charge that has that energy or is in a place, of that energy, like an equipotential surface or whatever, then that's what potential is. That's what voltage is. It's potential energy per unit charge. Now, if you're on an equipotential surface, that means all the potential energy on that surface is the same. That's what I was just describing in terms of property, right? It doesn't take any work to move it around. It's the same potential at every point on that surface. But what if, and you can say the same thing about a gravitational surface, right? That's why it doesn't move. The gravitational potential energy is the same. And we didn't define a gravitational potential, but I told you last week we could. And it would just be gravitational potential energy per unit mass as opposed to per unit charge. And that is the definition of gravitational potential. But the point is, it's energy per unit whatever. In the case of mass, object, it's, mass, it's mass, or matter, it's mass. In the case of electrons and neutrons, or electrons and protons, it's charge. Now, what if I come up and I do work on that surface and make it where there is a potential gradient, meaning the potential is not the same on the surface, higher here than here. Well, what we see is the mass tends to move towards a place of lower potential. That is lower potential energy per unit charge. Move down. Well, the same thing, the analogy we can make with charge. In a conductor, if you have no battery associated with it, every place in the conductor has the same potential. So the charge doesn't move collectively. When you put a battery, a positive in on one side of a metal and a negative, potential on the other side, it creates we call it a potential hill because we're making a analogy between a gravitational potential hill. And so it causes the potential to change, going from high potential to low potential. It turns out the function is linear. And so we can really think of it kind of like a sloped hill, but in terms of electric energy as opposed to gravitational energy. And so the charge, all the charge will flow downhill collectively from high to low. And that's what current is. So by putting a battery on an object, it creates this electrical potential hill, and the charges flow downhill. Now, a battery does two things. When say, well, and as we've said earlier, the only thing that actually moves in a conductor are electrons. So it's only the negative charges that are flowing from the negative lead down to the positive lead. For the negative charge, the negative lead is the high potential end. Think of like charge repel, so it wants to get away from the negative end and flows toward the positive end. Now, when the charge gets to the positive pole of the battery, it doesn't just stay there. The battery then takes that charge and places it back on top of the potential hill, and then it flows down again. So in terms of a battery, if this is an electron, I place a battery on a conductor, creates the hill, charge flows down, battery then takes it, puts it back on top of the hill, and flows down. And the battery just keeps doing that as long as it has chemical energy that's creating that electrical potential hill. That's how a battery works. When the battery dies out, the potential hill decreases, and the strength of the battery decreases, whatever its rating is. If it's 1.5 volts, gradually that begins to die, and that's kind of equivalent to thinking the hill is losing its slope, And ultimately, in fact, you can see that in my little lights here, they're kind of dimmed out. I usually have need to replace the batteries because the potential hill is so small that there's the current is decreasing. We'll talk about that and quantify it next chapter, quantifying the potential with current and all that stuff. But it's a linear relationship. The slope of the hill is proportional to the magnitude of the current, given a certain amount of resistance in the material. And that's something called Ohm's law. But yeah, so that's another way, a very pragmatic way of thinking about what voltage is, as opposed to just thinking about the definition, potential energy per unit charge. It creates an electrical potential hill in the material that negative charge can flow down. Okay, now, so I'm going to take this capacitor, and again, this is the symbol for a capacitor right here, and it just represents two metal plates. Now, unlike the battery, capacitor is somewhat neutral. Like once we charge it up, it will have a positive plate and a negative plate. But whereas the battery's poles are inherently positive and negative based on how it's designed with its whatever chemical compounds are creating the electrical energy. For a capacitor, it's literally just two plates in close proximity to one another that are not inherently positive or negative. But depending on how you place the battery in the circuit, when it charges up, it will store charge in such a way that one plate will become positive and one plate will become negative. And yeah. So in this case, I'm going to take a battery and there's one last symbol, and it's a switch, where you can switch something on and off. And a switch basically looks like this. Two poles like that. These are like poles. And when you close the switch, so this is an open switch, and a closed switch looks like this. I'm going to draw this just with a different color just to emphasize it. So this is open and closed. All right. So in my simple circuit over here, I'm going to have a switch. I have it open for now. I'll make a battery. Yeah, let's do it this way. Doesn't matter. So this is negative, positive. And up here, I'm going to put a capacitor in the circuit, large capacitor. So delta V for the battery and C for the capacitor. Now, when I close this switch, and we'll talk about that in a minute, the current will start to flow, but it won't continue to flow because capacitor, the nature of the capacitor. Also, I'll say this. This is an ideal circuit where basically it has no resistance. Whenever we place a resistor in we talk about basically the resistance we'll talk about it coming from just the properties of wire itself. And when we place a resistor in, it's just a bunch of wires. That's what this represents. A bunch of wires just kind of mesh together to increase the resistance of a particular wire, and then we place it in the circuit. And but basically the wire itself, just the one single wire that's connecting, so it's the same stuff, right? Because it's just made of it has an inherent resistance, which when we place a resistor in, we assume that the resistance of the resistor is much larger than the resistance of the wire of the circuit. So then the resistance of the overall circuit just becomes the resistance of the component resistor that we place in. And then we say that basically the wire itself has zero resistance or ideal. So no resistance at all. So ideal circuit. So whenever we don't have because the wire itself is ideal, with no resistance. Whenever we don't have a resistor in the circuit, it means that the circuit has no resistance at all, not even that of the wire. So that's why we say it's ideal. Now, only superconductors do that. And that's the whole point of superconductivity, is that it material that has zero resistance. This is not that. This is just a ideal scenario that we're starting off so that we can talk simply about circuit design, in the same way that we start mechanics talking about frictionless surfaces and then introduce friction later. So nothing fancy type of material that we're talking about. It's just an ideal scenario that we've broken it down for simplification. So an ideal circuit has zero resistance. Place that here. Zero resistance of the wire. All right. Time we got? We got plenty of time. So yeah. Where do I want to go from here? Oh yeah, properties of just qualitatively talking about charge moving. Now, I'm going to remind you here that the only charge that actually translates, I said move, I need to be a bit more specific than that. Remember, specificity is a property of class, a theme. All charge moves, even if there's no collective movement. The free charge is kind of jiggling around in place, but the average value of the position is zero. The atoms are connected to the sites, and I'm referring to the Einstein model. The atomic nuclei, I mean, they're also vibrating, right? And the electrons certainly are. They're not really orbiting around like the basic Bohr model implies that they are, but they're certainly not staying still. So whatever they're doing, however they're moving, and really it's quantum motion, right? Where it disappears from one spot and then finds it in one probable spot and then finds it at some other probable spot that it could be. And that's complicated. Okay, but it's not really like the Bohr model where we think of electrons orbiting around. They don't do that, from what quantum mechanics suggests. But the first approximation that we assume is that that's the case. Not assume, but that we speculate. And again, that's a simplification, just like a frictionless surface or an ideal. We know now, at least at the beginning, I thought they thought that was the way it occurred, but turns out it's not. And that's a really interesting point, actually. But I won't go on a tangent right now. Let's just leave it at that. So, yeah, so the charge, then we say that negative charge electrons are the only thing that actually translate in, meaning collectively move with in a conductor. Now, just hold your horses if you're saying, well, what about the positive charges? They move, and the book that says positive charges are, in fact, when we get to current next chapter, it's going to define the current in the direction. Now, current is not a vector, but it's the collective movement of charge. We'll define it as a scalar quantity. Now, current density is a vector, which is associated with current, but that's for a later chapter. But current, right now, we'll say, we'll qualitatively say it's always a scalar quantity. And it doesn't have a direction. But the velocity, the drift velocity associated with the current, and we'll talk about the relationship between current and drift velocity. It, in fact, does have a direction. So the current will certainly flow in a particular direction, even though we define it as a scalar quantity. And so when the book talks about the orientation of current in a circuit, either clockwise or counterclockwise, if we're looking at a two-dimensional representation of a circuit, which is what this represents, current will, in this case, the current will be defined as flowing basically from positive to negative. So it doesn't flow through the battery, it flows in the circuit, right? So technically in this circuit, the current, when it flows, will have a counterclockwise orientation. So basically, we say that current is defined as flowing in terms of in the orientation or the direction of the drift velocity of the positive charges. So if I'm telling you that the only thing that actually translates in a wire is negative charge electrons, then what the heck are they talking about? Like, what's going on? And for whatever reason, books don't actually get into this discussion. When you get into the chapter, they're just going to say current is, how it's defined, which is uh, basically flow of charge, so charge per unit time, delta Q over delta T. And they're going to imply that, that for at least in physics books and engineering books, they actually do that right. They define current in the direction of the flow of electrons. But in physics books, the implication, because we always like to do positive, we like go with the positive. So the implication is that we're defining the value, the quantity in terms of the positive charges moving. Now, as I've told you several times, the positive charges in the Einstein model, they are embedded in the nucleus, in the protons. And if they start to flow, if they start to move, translate, then that means they've broken their bonds. And what we kind of envision is the disintegration of that matter, just like in the Infinity Wars, and whoever that guy was killed half the people in the universe. And when they dramatize it in the movie, they things just kind of disintegrated like dust. That is actually what would happen if protons started to translate in matter. It would just disintegrate because they're in the nucleus. Those bonds are being broken. Since that doesn't happen, and since the book still talks about some positive charges flowing, what are they talking about? Get into it a little bit more, quantitatively in the next chapter. But for now, let's first establish that only electrons translate in a conductor, as in translational motion. And by conductor, I'm really meaning a metal. That's what we're talking about. Only electrons translate in a metal. And but we do have, so then, what do we mean when we say positive charges are also flowing? So like in this discussion I've been giving you, let's say that this ball is an electron. And let's say that this is the negative lead and this is the positive lead whenever I do my, make my, apply my battery. I apply it in that way. And so, um, the, actually, let's do it the other way. Let's make this the negative lead and this the positive lead. Because so this rim will catch the thing when it flows down. So I put on my battery, I create a potential hill, and the charge flows. Okay. Then the battery takes it, puts it back at the top of the hill, it continues to do that. So the electron flows downhill. So if it's flowing downhill, that means that this must be the negative end and this must be the positive end. It's easier for me to think about it in the context of the property of charge, that this must be the negative pole because the electron wants to get away from that negative pole, like charge repels and move down to the positive, and then the battery puts it back at the top. So when I close it, well, because I have a capacitor here, it's not actually flowing all the way down. This is for like a completed circuit is what would happen if there were no capacitor here. The you know, I guess kind of like just what I'm trying to all this stuff is ideal. So anything that I draw is not actually going to be ultimately what we're going to use for the circuit, because we're using an ideal circuit, so there's no resistor. And that's why I don't really want to draw it, because I don't want to put it on the board and you look back in your notes and maybe forget something I said, because it's ultimately when we get to the next chapter and we have these things in after defining them, we won't be drawing them separately like this. That's one capacitor, and that's the only thing in the circuit. That's an ideal situation, so that won't exist. I'm just doing it here just so that you can, just so that we can simplify the situation. So basically, if you can imagine a wire with nothing in it, no elements on it connected to a battery, then there's a completed circuit once you close the switch. And so, and that's the scenario that I'm talking about, where the free charge would just start to flow downhill, and then the battery will put it back at the top and it'll continue to flow. Now, what I'm getting at here, the point that I'm trying to make is that when we define a positive charge flow, and the book is not going to tell you this, for whatever reason, they don't say it in sophomore level physics books, you know, intermediate level, like this book. They don't really get into this discussion, and I'm not sure why, but otherwise, for me, it was very confusing, because a lot of the implications of what we're going to talk about with the capacitor literally do not make sense unless it only makes sense if you're assuming that there are actually positive charges flowing. I don't like to do that because they're not, right? It contradicts everything I've been telling you, and it's also not true. There are no free positive charges. The free charge in a metal, it's all negative charges, because, and I think you know this, right? Because some of you, that when the thing gets together, when it combines, it's the electrons in the valence level that pops off, you know, one electron gives. So all the Fermi electrons that are, you know, free to move around, they're all electrons. There's no positive charges there at all. The positive charges are in the nucleus, right? Because once that atom gives up the electron, it's not positively charged. But that's because there's more protons in the nucleus than there are electrons around the electron cloud. So the positive charges are in the nucleus. There are no positive charges in the Fermi sea, okay? So you jump to the average physics book and they start talking about current and resistance, and all of a sudden we've got these positive charges flowing that we're defining current, and nobody says anything about it. It's kind of a pet peeve with me, because I think I was probably like a senior before, and even then I don't think I knew something was going on. I didn't really fully figure it out until graduate school. I just sat down and started thinking about it one day and just figured out an argument, because I had to teach it to somebody, and someone asked me, like, where are the positive charges, and I looked like an idiot because I did not know, right? That actually happened in undergrad when some student was asking me. I was tutoring them. Anyway, I was like, duh, I don't know. And so now I know. And this is the argument I'm giving you. Maybe because it's a lot, it takes kind of a while to explain it, and it's a lot of ink. I don't know. I have no idea why they don't talk about it. Most physics books don't. But clearly you can see it still upsets me. But this is the deal, that in physics, because of the concept of charge neutrality, and you have to just think about what I'm about to say. The protons are definitely not moving. So think about this. Just think about this surface as you know, it's full of, this is just one, but it's full of all of these. I know it's two-dimensional, but whatever. This is like an area, a volume that incorporates free charge in the metal. And it's just all electrons. And yeah, that you could envision, just, you know, the Einstein model, just envision that in your mind. We have to get to a place where we're using these thought experiments now. And we know that, just think of that three-dimensional lattice that's here right in front of you. And this is just one of the electrons in the Fermi sea that are moving all around in the electrons, you know, all around the volume in between other electrons and other, atoms, and the Hooke's law springs that are holding the atoms together, whatever the things that bond the atoms, the nuclei, atoms. And we're kind of making it, cross between a three-dimensional and a two-dimensional representation. Because, how do you make a hill in a three-dimensional? I guess you can, but whatever. So what is the direction of the flow and I know all that doesn't really kind of answer all those questions, but we don't need to, because we're just kind of making an analogy. The battery causes the collective flow of all these electrons, well, down the hill. And then collectively the battery puts them on top, doing that. But if you were to say that, okay, once I place that battery on, kind of think of it like this. So we know that the object is neutral. It's neutral because it's still neutral, even though the valence shell gives up an electron. Because collectively speaking, all the atoms now, which are positively charged, once the metal combine, they still don't have a field, doesn't give off a electric field, because the electrons kind of move in the sea, and even though they're kind of shift, and it's not like they're flowing around, because that would be current. They're kind of like, there's no average value of the movement. So when we say they're shared collectively, it's not like it's not flowing like a sea. That's kind of a misnomer. It's just they're vibrating, but there's no collective movement, and they're still shielding all the atoms so that there's no field, no localized field, and still the total number of electrons and protons in the whole thing are equal, so it's still neutral. But when we put that battery on, what it would look like is now we have current, and the word is actually coming from like currents in the sea. So now there is a collective movement of charge, and it is collectively flowing like current in the sea, and we call it current. And so what we see are negative charges that are flowing downhill. But if this were kind of like a fountain, think of a fountain where there's water, stagnant water, and then you turn on the fountain and the water starts to flow, and then it kind of falls back in, and then the motor, takes it in somewhere inside the fountain, brings it back in, and causes it to shoot. And so the stagnant water is there, but the water is flowing. So there's a non-zero flux, right? We define flux. There's now a non-zero flux because the water is flowing through, you could describe a cross-sectional area someplace, but it's non-zero. Well, think of this, if before you put the battery on, the object is neutral, so clearly there's no flux, because nothing is translating. But then you turn on the battery, and now you have negative flux, negative simply because the negative charge is moving. That would violate the concept of charge neutrality, because it would look like, the material is no longer neutral. Because if it were neutral and it had the same number of positive and negative charges, and if voltage is supposed to affect positive charges in a similar way that it affects negative charges, and it is clearly affecting the negative charges in such a way that they are flowing now, then why aren't there positive charges flowing also, i.e. in the opposite direction? But they still should be flowing. But there aren't, because they are in the nucleus and they physically can't. So what we say is that there are something called holes, Holes, which essentially are the absence of negative charges, which means, sorry, not the absence, the opposite of negative charges, and absence, but flowing in the opposite direction. So in this space, right, where this electron is considered neutral, not because there's another positive charge in that space, but because there's a proton down in the nucleus that can't move, but overall its collective charge is neutral. So we kind of say like a hole is kind of like a ghost particle, but the opposite of a negative charge. And it's not antimatter or anything like that. This is a purely mathematical construction that we create just to make things make sense. Because we can't really talk about the proton here, the positive, because it's down in the nucleus. It's not going to be, it can't do the same thing that this electron does, particularly once we put on the voltage and the potential difference, and we see the negative charge respond to that. So when I put this potential hill on and this negative charge starts to flow, it would kind of look like, if you could see the places, it would look like negative charge just popped out of thin air and started to flow. That's what it would kind of look like the case if we didn't create these holes. But if we say that mathematically the holes were already there causing the thing to be neutral, then when the negative charge starts to flow down the hill, the hole, the absence of an electron that is also positively charged, moves up the hill. So you have like a positive and negative charge coming from the same place. So therefore, starting from the same point. So therefore, it doesn't violate the idea of charge neutrality. Yeah, that's the thing. I'm not kidding you. This is actually the argument, and it's the only argument you will come up with to make sense of this. And to make matters even more complicated, as I told you, in physics, when we then define what the current is, we don't define it in terms of the real thing. We define it in terms of the mathematical construct, the whole moving up to and that's the direction of the actual current in the circuit. I kid you not, that is actually what's happening. Now, you would think that when you look at that chapter and they're telling you that positive charge, that they would explain all of this, but no, they do not. They let you think that there are actually positive charges that are flowing in the thing, in the conductor, and that's how we define current. I don't know why. It's just convention, and I don't know why it's not explained, but this is the explanation, and this is the only explanation that you will ever find, and you won't find it because it's probably, I don't know why, but whatever. This is valid because there are definitely no positive charges flowing in any metal anywhere ever. So, and then to make, as I said, to make matters worse, we actually define the current in terms of the hole and don't even tell you that it's a hole. We just say it's a positive charge. And what's even more confusing is that you would think, okay, if you have negative charges flowing down the hill and positive charges flowing up the hill, then is that double the current? And the answer is no, it's not double the current. You know why? Because there's no positive charges actually flowing up the hill. That's why. It's only electrons flowing down the hill. So there's only one current. And yeah. So we have to keep all of that in mind in this discussion that I'm about to give you here. Okay? Keep all of that in mind. We'll come back to it, as we get to the end of it. I just wanted to start with this concept of a hole, Hole. It is the absence of a electron, but has a positive charge. So the concept of a hole. A hole is a non-existent or non-real mathematical construct So by construct, I mean mathematical construct, non-real charge which is the absence of a negative charge and has positive polarity. And I don't want to just say opposite of a negative charge because that implies something that's, has mass, has matter, that's real. And it's not the opposite of that because it's not real. So I just say absence of a negative charge. With opposite polarity. Okay. So a whole is a mathematical construct non-real charge which is the absence of a negative charge with opposite polarity. Okay, yeah. Holes flow opposite the direction of electrons. And when I say negative charge, I guess I just specifically say electrons because that's the only thing that's negatively charged in a metal. But I'll say free electrons because they're not opposite the bound electrons. So absence of a free electron. The opposite polarity. Holes flow opposite the direction of electrons. All right. All right. So that's a basic, I guess, understanding of these fundamental properties associated with circuits, and these things we'll be applying. We're going to add them to our understanding of the Einstein model, which I've tried to incorporate qualitatively here in this discussion. And we will move forward over the rest of the semester with this, adding this to our basic understanding of visualizing a circuit. So now you can see why I start the class with this idea of the Einstein model, because it would be very difficult for me now to introduce the Einstein model on top of all these other things I'm trying to talk about. But now you've had, I guess, 7 weeks, 8 weeks going on with this. So this is the 8th week to kind of incorporate and let this idea of the Einstein model kind of incorporate in your mind. And now you're acclimated to it, right? So you have an intuition for it. And so now I'm adding things into that, qualitatively, that is, as to what's happening inside the circuit. Now, again, this is a wire here. And I'm saying the Einstein model, like this lattice of atoms. If I blow this wire up, it has a cylindrical kind of, like if I make it large, it's basically like a cylindrical wire, right? If I blow it up. So inside that thing is where I'm saying we're inside that. And where the Einstein model is applicable inside. And remember, just so you remember, right? Einstein model was this thing that we created, this lattice of atoms. Now, I wrote it as a 2-dimensional thing, but you could kind of make it a 3-dimensional, box, right? Where this is just the front face. You can think of it like that. Well, and we had other things we added onto this. We got the Hooke's Law springs. So it's this thing that we did at the beginning, like the first week, the first day, actually, I think I did it. And then we had the bound electrons here. And so these are the bound electrons around that, like the electron cloud. And then we have the Fermi electrons. Now I drew them like this, kind of implying that they're flowing through, but they're not flowing. They're just electrons that are just there, and they have their own average vibration, and they don't, as I said, the average value is not moving, but I don't know a way to draw that. And also because I refer to it as a Fermi C, and C implies current, which we will have current if we have a voltage on it. But in general, there's no current, they're just there. So these are the free electrons here. So I think I refer to it as E free, that's these guys. And E bound are the electrons that are still in their, in their shells around the atoms. And of course, these are the atoms, black things, and protons, neutrons inside there. And this whole thing is called a lattice, an atomic lattice. And these guys here, these squiggly blue things, those are the bonds. And we approximate the bonds from a mechanical point of view as springs, which we represent as K delta X. And, as these atoms are vibrating, the average value of the spring is changing, it's oscillating back and forth from its equilibrium position, and actually can be approximated as a simple harmonic motion. So all that stuff is what we talked about before and now. So that whole lattice, that is what's inside this wire. So these free electrons, when we close the circuit, those things are the things that actually then begin to flow. So it's like the electrons then will move, basically in the clockwise orientation about the circuit, move in the way I've just been describing. Now, I'm going to go ahead and say that, current will be flow in the opposite direction, because as I just told you, to make it even more confusing, as physicists, we ignore the electrons, and we say that there's positive charges flowing in the counterclockwise direction. And my explanation for you now for that is that it's actually nothing flowing. It's just the absence of electrons that have the same polarity that we call holes, that we treat like positive charges flowing. We treat them like real things. And that's the thing that's flowing. I know this, like when I kind of stand back and listen to it, it sounds ridiculous. And you would wonder why, if it's this complex, why that, when you get to it in the chapter, no one will actually tell you this. I don't know. I keep saying this over and over because even after 40 years, it baffles me. I have no idea what the convention is about this. And just because I write it here and they don't say it in the book, it sounds like I'm just making this stuff up, and I'm not. This is actually the only explanation. So, just a second. Oh, hey man. Oh, you know what? I left town. I forgot to do that. I will go. I will do it today. Yeah. Yeah. The work order thing. You what? You right. Okay. Oh, you did? Oh, good, good. All right, cool. Thank you. I appreciate it. And sorry about that. Yeah, I was rushing to leave town, and I got hey, I'm good. I'm good. Good. Yeah, yeah, yeah. And you can come in. I'm teaching the class, but it's all right. Yeah, come on in. Yeah, 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 yeah. Whew. Just a second. I got an apartment inspection for a second. Thanks, man. Take care. Have a good one. Yep. Yeah, I had a quick routine apartment inspection. So what was I saying? Oh, free charge, positive poles. Yes, got it. So yeah, I'm not lying to you. This is actually the explanation. And there are holes, and they're not real. They do flow around the circuit. At least we assume that we describe them as such. Okay. So the final thing I want to say to you is another, as I told you, we have these different perspectives. And one perspective of thinking about why current flows whenever you close this battery, close. Oh my God. Let me have the spontaneous voice activation of my iPad whenever I mute it or whenever I close it down. Actually, yeah, I should mute it. Keep it open and mute it. Oh, oh, there's one thing that I need to do real quick. All right. as I was trying to say, a lot of drama in the apartment today, in the building, but good drama. There's another perspective about why the charges will flow once this circuit is created, and it's another thing to think about, and it's also true. Whenever I close the circuit, well, we know this. We actually know it from what we discussed in the last chapter. Again, delta V is equal to negative E dot dl or dr. So we know that if there is a non-zero if there is a potential difference, there has to be an electric field associated with that. Otherwise, the potential difference will be zero. So we can think about the potential difference in terms of its energy per unit charge, or we can think of it in terms of the field associated with the potential difference. And there's even another perspective, and I told you that as well, that E is defined as F over Q. So if we substitute this in here, we can then associate the potential directly with the charge, with the force. It's equal to a negative 1 over Q integral of E dot dr. Sorry, F dot dr, because E is equal to F over Q. So we can associate the potential with the field. We can associate the potential with the energy, the potential energy, or we can associate the potential with the force, the conservative force associated with that electric field. The point is that I'm trying to get to qualitatively is that whenever I close this switch, I can also think of an electric field being created in the wire. A constant electric field is created inside this wire, and it points. All electric fields always point from positive to negative. So, if I think of the Einstein model, like by blowing up the wire and think of all this, like this lattice inside the wire, in my mind, I envision a constant field that's actually pointing inside that wire as well. So like the way it would look here is the field is pointing in the direction of the positive charges, the holes flowing. So inside the wire, once I close that circuit, there's a constant electric field pointing in the direction of the current. And that's actually what makes the charges. You get like, because there's going to be a force associated with that electric field, and that's what's causing the charge to flow. And again, it's just a different direction. You can either think of it as flowing downhill from high to low energy, right? Because that's, or you can think of it as a force causing it to flow once you put that battery, and that force is the conservative force associated with the conservative field, electric field that's set up in the volume of the wire, the space of the wire, due to that battery being connected. Two different perspectives to explain the same thing. Now, positive charges flow from positive to negative, but negative charges flow from negative to positive. Sorry, yeah, negative to positive. So it's kind of like salmon flowing upstream. Even though we define the electric field as pointing in that direction, the negative charges actually be moving upstream. Yeah. All right. So all of those things are true. All these different points of view about what's happening inside a metal when you apply a voltage. All right, so let's come back and talk about this capacitor specifically. and talk about how it's charging up. Well, I guess I can leave these things. Let's just come over here. I've actually already started. Remember I told you that these plates are also metal plates. And I've drawn this segment, really, it's blown it up as a segment in the wire, but really I could have drawn it going all the way flush to the plate. So that electric field, it actually terminates on that plate, like, but right down at the point there, whatever. So if this plate was a neutral plate, but when I close the switch, it now sees an electric field. What I like to think of is, I like to think of it as pulling off a hole. So this, well, I guess, yeah, either pulling off a hole or depositing a negative charge, either the way you want. Yeah, I guess really, um, yeah, maybe I should say that from the other side, but yeah, since the electrons are the only thing that translates, then I'll say this. If you go to the other side, the other plate over here, if I blew it up, basically everywhere the electric field is pointing in the same direction. And even in between the plates, it still starts to build up. But immediately we're going to see an electric field in the wire. So what you want to think of, one way that you could think of this is that, that, yeah, just we're looking at it from that perspective. And it comes up there. Yeah. So the electric field, I guess, would still be pointing in this direction. So electrons flow from negative to positive. So whereas this plate was a neutral plate, when I close the switch, the electrons, they want to move down, flow down the electric field, flow in the direction opposite the electric field. So I think of it as these negative charges, these electrons, Fermi electrons on the plate, they're pulled off, sent around. So they get down to the bottom of their potential hill, which is here, but then the battery puts them right back at the top, even though they didn't come from there, and then shoots it back around again. If there were no capacitor here, it would just continue to go all the way around. And there's, like I just told you, illustrating on my chair there. But with a capacitor, there's a space between the gaps, and the electrons can't jump across, right? It's literally a space. So they're pulled off of one plate and deposited as excess charge on the other plate. When they're pulled off of this plate becomes positively charged because it was neutral before you pulled the electron off. So it becomes positively charged because there's a hole, people you can think of as a hole being deposited on it, but a hole is nothing, right? So there's no charge being deposited. That's another thing that's confusing about when you read it in the chapter. They say that there's positive charges, because where do those positive charges go that they talk about? Well, they say positive charges are deposited on the positive plate and negative charges are deposited on the negative plate. Well, yeah, holes are deposited on the positive plate, but the holes are nothing. So how do you justify that? How is nothing deposited on the plate? Well, it's deposited because you're actually pulling off an electron and leaving it positive. Why? Not because there's some thing that was put there. It's because actually the proton down in the nucleus on that plate, now, there's more protons and neutrons. And if you pull off an electron, that leaves it as one positively charged. And that justifies how the whole, which is nothing, can be deposited on the thing and then it become positive. Kid you not, that's what's going on here. And they say nothing about it. All right. Electron comes around, which is a real thing, goes, puts on the battery, puts that, goes at the top of the hill, then goes around, but it can't go any further because it gets stuck on the plate. So the only thing that's actually deposited, and here's the key. I'm gonna ask you about this when I finish this whole discussion. Here's the key. The only excess charge that actually deposited on the capacitor, even though it has two plates, the only thing that's actually deposited are negative charges that are deposited on the negative plate. And as that, and so it starts to charge up. And as it charges, the electric field that was kind of instantaneously created in the wire when you close the circuit, it starts to build up on the conductor, on the capacitor, as these charges are created. And again, electric field is defined as pointing from positive to negative. So that's the E that begins to create, and it's going to build up to a maximum field, which will be equal to the maximum field, the magnitude of the field inside the wire. I want to make this charge a different color. Make it purple. And so, so the first negative charge that's deposited on there, it doesn't feel any kind of resistance or anything because there's no charge on the plate. But and think of it as property of charge. But then I pull another electron off of this plate, send it around down to the bottom of the hill, put back on top, and goes around, gets deposited here. It's a little bit harder because now it sees a negative charge that's already there. So the battery has to do a little bit more work to get it on the plate because now the capacitor is being charged up. And also a little bit more work to pull an electron off because this plate is now positively charged, so the electron doesn't really want to come because it's now attracted to that plate, but it's attracted more to the battery than it is to the capacitor while the capacitor is charging because the battery has a larger voltage. And it's pulled around. And now you also begin to see a voltage on the capacitor, right? Because it has now a positive and negative plate. So there's a delta V that's increasing as the capacitor is increasing. So we've got three things increasing on the capacitor as it charges up. The one is the charge is accumulating, right? We've now defined a positive plate and a negative plate, Q positive, Q negative. Remember, Q negative, Q positive. And so we've got charge building up. We've got an electric field building up in between the capacitor plates, E. And because of that, we have a voltage, right? Because and they're all related through these relationships here that I've said, right? They're all related. And that just keeps happening. It keeps happening until the capacitor is fully charged. And when will the capacitor be fully charged? Well, let me ask you this. If someone were in class right now, I would ask you this. How does the polarity of the field of the capacitor or the polarity of the voltage, of the capacitor, how does that compare to the polarity of the voltage of the battery within the circuit? Think about that question. How does the polarity of the voltage of the capacitor compare to the polarity of the voltage of the battery within the circuit? When I say polarity, I mean really orientation, I guess I should say, but it's associated with polarity. Polarity is positive or negative. Orientation is clockwise, counterclockwise. What I'm getting at is that the battery is situated in such a way, its polarity is situated in such a way that it is creating current, remember we're following the holes, in the counterclockwise direction. It's making current flow in the counterclockwise direction. The capacitor is stopping that current, doesn't completely flow because the charges are stopping being charged, being piled up on the capacitor plates. But
I guess one way to think about it is this. What if I were to open the circuit, take the battery out, and then close the circuit? What would happen to the charge on the capacitor? Well, it would flow off because there's nothing to charge it up or nothing to, balance it, keep it, keep the charge there. It would kind of act like a battery. And what would be the polarity of the charge of the current due to that capacitor? Well, if we're following the positive charges, the holes would want to flow in the clockwise direction. So the polarity of the voltage of the capacitor is opposite that of the battery. So now let me open the circuit, put the battery back in. That's still the case. As the battery charges up a capacitor, it charges it up in such a way that the capacitor has opposite polarity to the battery. That is, the capacitor is fighting against the battery or vice versa. And that's just natural physics, how it works. It always works that way. A capacitor will always charge, a battery will always charge a capacitor with opposite polarity of itself. That's just how it, based on what I'm explaining to you, how it does. So the answer I was looking at is that it's opposite polarity. And that helps to give you understand why there must be an upper limit for the capacitor. How much voltage, how much charge can be stored on the capacitor, and what will be the maximum voltage associated with that stored charge? Well, the answer is obvious just from looking at and understanding what I'm describing here. It's the battery that's causing charges to be pulled off and deposited on the other side, and it's getting the energy to do that from its voltage. Why? Because voltage is energy per unit charge. And it's showing you how much energy per unit charge these charges have as they go through this process. The electrons being pulled off and deposited on the other side, and the holes being deposited on the positive plate. This is the amount of energy per unit charge. What? The voltage of the battery. So if it were 5 volts or 1.5 volts, the energy per unit charge of each charge as it moves around the circuit would be 1.5 volts. That's really the meaning of voltage. You start to see it now when you apply it to a simple circuit. So the point I'm trying to make is that since the energy, if you think of it, whether as you think of it as energy per unit charge, voltage, or if you think of it as total potential energy, total charge times the voltage of the battery, meaning total charge on the capacitor plate, because you can think of it like that, right? You just, if delta V is equal to delta U over Q, then delta U, the total potential energy stored in the battery, is going to be equal to the voltage of the capacitor times the total charge on the battery, on the capacitor, right? Or any, version thereof, as it charges up. So basically, the capacitor is getting its energy per unit charge from the voltage. So it doesn't make sense. So what is the maximum voltage that the capacitor could be? Logically, it has to be that of the battery, because it would somehow be a violation of conservation of energy if somehow a battery that has voltage delta V could charge up a capacitor such that the voltage of the capacitor is larger than the voltage of the battery. That doesn't even make any sense once you think about it and you understand what's actually happening here. So the voltage of the capacitor could be anywhere from 0 to delta V being the voltage of the battery. And that's the maximum voltage the capacitor could have. And the maximum charge on the capacitor will happen when its voltage is equal in magnitude but opposite in polarity within the circuit of the battery. And by the way, that's also when it's going to have the maximum field, whenever the voltage is maximum. And you can see that from this relationship. Delta V equals minus E dot, integral of E dot dr. So it just continues to do that until the capacitor is fully charged, and it's going to be fully charged at this point right here when this thing is delta. It's delta V, and it's maxed out. It'll have its own E field, and the voltage will be, so this, the negative plate is V minus, the positive plate is V plus, and so then the delta V here of the capacitor will be equal and opposite to the delta V of the battery. And that's how you charge a capacitor, how you do it. And it's interesting that once you charge a capacitor, it will stay charged. You can actually open the circuit, take the capacitor out, put it in another circuit, or do whatever you want with it. And it generally, ideally will stay charged until you put it into a circuit where there's a disproportionate voltage in that leg, and it will discharge. And basically when it discharges, it acts like a battery. Now, a couple of chapters from now, we will look at that again. We can derive the functional form of the discharge. We can talk about how a capacitor charges and discharges in a circuit. And we will work out that problem using separation of variables, which I guess I can review that for you. We'll do it then. So that's it. That's what a capacitor is. That's how it works. Now, I'm pretty sure I've given you a whole lot more detail than what's in the book. For me, this is a kind of a larger discussion. I take a lot more time doing this than what the first couple, because it only gives you like a page maybe in the book there, the first couple, and just defines, which I haven't done yet, but I'll define capacitance here in a minute. But for me, this discussion is imperative. It's imperative. I kind of equate it or put it in the same category as describing the Einstein model, and it's really a continuation of that discussion, none of which is in your book. Because as I mentioned several times, I believe I need a picture. I need a visual. I'm a visual learner. I need to understand what's actually happening. I got to see it. And if I don't, it just handicaps me in ways that it's kind of beyond the scope of this discussion. But I've got to be able to see. If I can see it and I can tie up all the loose ends, both qualitatively and quantitative, you use calculus is easy. Math is, once you understand math, it's easy. It's discrete. It's definite, right? It either is or it isn't. But the universe is not that cut and dry. So, and when you start to make qualitative discussions and qualitative descriptions, for me, the math is not enough. It's enough to get answers, but it's not enough to understand the answers. That's the point I'm trying to make. And I need to understand them. Otherwise, there's a problem for me. So the visuals help me to understand. And so this is the discussion that how I justify all of these things. And yeah. So I hope this helps you. And your ability to make sense and actually visualize what's happening in these circuits. 6 minutes. So the final thing, now that I've explained all that, the only thing left to do is to just describe or define what capacitance is. And capacitance is simply just a ratio. It's just a mathematical ratio. In the same way that when we take like the Pythagoras, because in these triangles that he saw, these right triangles, no matter what the lengths of the sides are, you saw these ratios that were significant: cosine, sine, tangent. They're just fractions, right? The fact that he called them this cosine and thing, that's also something that kind of, I think I mentioned that in mechanics. I didn't really understand what they were. And, like, even though I knew the definitions mathematically, it wasn't sinking in because it just looked so funky. Why do you, why is it a cosine? Like, what is that? What cosine is? It's because we call it a function. So it's like the angle is this function, like what is it's doing something? What is it? Like how is it calculating this thing? This you put the angle in this function. What does the function look like? And the problem is that it doesn't look like anything. It's just a name. It's not, we call it a function, cosine, sine, tangent, thinking that the cosine represents some complex mathematical thing that when you put that angle in, it computes it and gives this thing. No, that's not what it is. I don't know why. Well, I'm not going to question him because he was a genius, Pythagoras, but for years, I thought that's what we were talking about. And even though I knew the definition, cosine is adjacent over hypotenuse, it just wasn't registering to me. It's literally just a name that we write that way. We're just naming the ratio of the sides of a right triangle and giving a relationship with the angle. And I guess you couldn't just say it's an angle, I guess. I don't know. I don't know why you couldn't do that. I guess because I don't know. Maybe there is still something I'm missing. Um, I guess, yeah, because if it's just an angle, then how would you distinguish, adjacent side over hypotenuse versus, opposite side over hypotenuse? You got to name it something. And so, but it is associated with the angle, so then you got to put something. Yeah, I guess that's it, but it's literally just a name that we then call a function. Why am I getting off on that tangent? Well, because the same thing applies here. Capacitance is just a name of the ratio that I'm about to describe to you. And the ratio, when you go back to this capacitor, the ratio is literally just, because what we find is that, so we can talk about the maximum voltage on this capacitor, and the maximum voltage, what we say is that the capacitance is equal to, we define the capacitance as the ratio of the total charge, so we can say Q total, to the maximum voltage, which is going to be the voltage of the battery, as I just explained, delta V. But the reason that we define it is that it doesn't, even as it's charging up. So when there's some delta Q on here that's not fully charged, say delta Q1. And I could have done it as I was charging when I had just the one charge is distributed, the positive over here and then one negative over here. Let's say that's a delta Q1. Well, it's going to have a voltage associated with that delta V1 and an electric field associated, delta E1. But then in the next instant, when there's another packet of charge or one charge, whatever, that's deposited, that's also going to be a delta Q2, which will have its delta V2 and its electric field 2 associated with it. What I'm trying to say is that even though those values change, what you see when you actually measure is that the ratio of the charge to voltage is a constant, and it never changes, no matter what the amount of charge stored on the capacitor is at any given time as it charges. It will have a specific voltage such that when you take the ratio, it will be equal to the same number. And that number we call capacitance. So you can make the same mathematical argument with similar triangles for right triangles with the definitions of sine, cosine, tangent. That's what Pythagoras did. That's why he named them something. So again, we're seeing the symmetry, mathematical symmetry, if you will, in or logical symmetry in physics associated with and geometry and mathematics associated with these. So that's why we name capacitance, because it is a constant ratio of charge to voltage as a capacitor charges up. And that's significant for us. And so we name it in the name. And so capacitance then becomes the constant of proportionality between the charge and the voltage as a capacitor charges up. That's significant. I should write that down. You should get that. What is capacitance? What is it literally? What does it mean? What is it physically? It is simply the constant of proportionality between the voltage, the charge and the voltage as a capacitor charges up or charges. Okay. And I will let you go right now, but I'll say one last thing. This has a significant implication, this last statement that I made, and this is a definition, by the way. So this is 3 equal signs. So the definition of capacitance is, I gave it specific values here. I was implying specific values, but in general, we just say capacitance is defined um, as really a delta Q, but I'm going to just call it Q over delta V. And you might see delta Q some places, but these are the symbols I'm using: Q or delta Q. Q or Q over delta V. Delta V is always written as a delta V because of things I mentioned earlier. But that's the definition of capacitance then. And and lost my train of thought. Oh yeah, the last thing is that we can write it as solve this for well, we like to write these QV diagrams, and usually it's done with I guess it's done with charge on the because the charge is the thing that we control. Well, right? What? No, voltage is the thing we control. QV diagrams. So is it charges on the? I mean, you see it done different ways, I guess, but I think we could ramp the voltage. So if we had a variable voltage here, yeah. So I guess voltage would be the independent variable, and charge is the dependent variable. If that's the case, then we could, yeah, I'm gonna go that route. So we could write this as Q is equal to C delta V. So then if I plot this, we see that it's a linear relationship between the two because of that definition. So if I have delta V on the x-axis and Q on the y-axis, then I'm going to get it's always going to be a linear relationship. But in that case, the slope of the curve will be the capacitance. So there's actually a way to test that in the lab where you can get a variable capacitor and you can just change the voltage on it and see change the voltage on this a variable voltage source here and change the voltage and then you will get for particular values of voltage you're going to get different charge on it. And the way you could do that is you measure the voltage on the capacitor to make sure it's the same the voltage as you're getting here, and then you could use this relationship. I guess if you wanted to measure the capacitance, you could have to have a something over here to determine the charge, which I guess there are devices that do that. Or if you know the capacitance, then you could figure out what the charge is specific to that voltage. I don't know, there's a couple of different things you can do, but the point is that if you assume charge is the dependent variable, then the slope of the curve, you can see it here, this is delta V, and this is delta Q. So the slope of the curve then is going to be C, the capacitance. So slope is equal to delta Q over delta V, and that slope M is equal to the capacitance. So, you could get a series of data points. Basically, it might look something like this. And it's a, average line, linear regression. And you can extrapolate the data and get the least square fit, and then experimentally determine either what in this case, I guess, if you're solving for capacitance, what the capacitance is. And yeah. So, constant of proportionality implies a linear relationship per the definition here, which is something that is very testable in the laboratory, and turns out to actually be valid. Okay. Actually, I think I might have gone over. Well, what did I have gone over? So I guess I made up that time, a few minutes. I'm going to stop it there. I guess on Wednesday, when we come back, I will continue with capacitance. A lot more we want to say about capacitance. I probably should do, actually, you know what? I actually started the lecture because I did a little bit of work there at the desk before I started. I think I started the lecture about 30 minutes late. It was like 8:30 or something like that. So I'm gonna take like a 3-minute break. There's nobody in class, so it doesn't matter. Take a few minutes. This is actually the completion of my introduction for capacitance. This is my introduction. This is where I stop for my introduction. And the next thing that I like to do is derive the equations for capacitors in series and parallel. Since I'm going to take another 20 minutes, it'll only take me less than 20 minutes probably, but I'll expand to 20 minutes to give you some explanation. I'm going to go ahead and do that. So I completed a minimum of what I wanted to do today. And as I said, this is always, a lot of people just do this introduction in like 10, 15 minutes. But I don't, because I have all these other things I like to talk about in the context of what I've been building in this course in terms of your intuition and visual. And so it allows me to talk about all these other things like holes and square that up with the Einstein model and all this stuff that I've said. And it helps with the discussion of a capacitor. Now, the question I want to ask you is, we have the charge on the capacitor. It's fully charged, which means that the negative plate, if you actually take a meter and measure, you will have minus Q charge on the negative plate of the capacitor and plus Q charge on the positive plate of the capacitor. So my question to you is, what is the total charge on the capacitor? And you've got one of three possibilities. I'm going to give it to you here. Well, positive and negative cancel and zero. So zero charge on the capacitor, which, by the way, it makes no sense because we said we were charging up the capacitor. So if you charge the capacitor, you got zero charge. What's the point, or what? Like, what gives? So logic, just based on definition, should tell you that that's probably not the answer. But then you got two other possibilities. If you're just dealing with absolute value, then you got Q on one side and Q on the other. And so the total charge could be, would be plus Q, or plus 2Q, excuse me, or sorry, 2Q. Seems reasonable. Or I guess you could just say Q. Why? Because we were charging up the capacitor, and also because, well, that's what the book says. It says that when you look at a capacitor, it's going to tell you that the total charge on the capacitor is Q, even as it tells you that one plate is negatively charged and the other plate is positively charged. So what is the charge of the capacitor? And more importantly, why? Why is that the answer? Well, I know nobody's in class, but while I erase the board, I'm going to let you think about it and then try to come up with an explanation. Then I'll tell you so we can move on to the other thing. Yeah. Okay. 0Q or 2Q? I've already told you what the answer is. The answer is just Q. The total charge on the capacitor is Q. And as I told you, it's from the thing I just erased, the total charge Q is equal to the capacitance times the total voltage, the maximum voltage on the capacitor, which would be equal to the voltage of the battery, delta V. So basically, you could say that the total charge on a capacitor is going to be equal to the voltage of the battery times the capacitance itself. It's always going to be that. The maximum charge on the capacitor equal to that. Because the max, delta V max of the capacitor is going to be equal to the voltage of the battery when it's fully charged. Well, we're talking maximum here, so yeah, that's implied. So why? Why is that? So that goes back, that's the justification for my argument for holes. Remember I told you that holes, these positive charges here, they're not real. They are the absence of the negative charges. So when they are moving around the circuit, there's nothing there. When they are deposited on the circuit, on the thing, they're not really deposited. Nothing is deposited. What's actually happening is electrons are being pulled off and sitting around the other side. So when you look at both plates, and when we talk about charge, we are implying excess charge, right? Because that's how you charge something. You put excess charge on it. We talked about that back with, when we talked about charging by conduction and induction. It's just that what's a little tricky about it is that when we talk about induction and conduction charging, I had a charging rod that I charged elsewhere. I didn't tell you how I charged that. It doesn't matter. We come into the conductor with a charged rod, which is a metal rod that's actually has excess charge on it. And then we, put it in proximity, either by touching or close proximity of the isolated conductor, and all the magic happens that we talked about before. But we didn't really talk about how we charge the charging rod. Well, here we're charging the capacitor with excess charge, and we see where the excess charge is coming from. It's actually coming from the other neutral plate on the other side. Now you might say, well, if it's a capacitor, how can it charge itself? Well, I don't know what to tell you. This is what it does. This is how we define it. Two plates are separate, put in the field, pulls off a charge from one side, puts on the other side. Well, it certainly is excess charge for that side. So it's excess charge. And we don't count this as excess because it's not excess. It's not actually something, as I said several times, it's not actually positive charges being deposited on the thing. It's holes. And what are holes? Mathematically construct of nothing. So what's actually, where are these positive charges actually coming from? They are the positive charges in the protons of the now, well, the protons were, they are basically, for that surface, it was a neutral surface that had the same number of electrons and protons. When I strip off an electron, that means that there is one less atom covered, or one less proton somewhere in a nucleus that's covered or neutralized, I guess is the word. And so now the total plate is positively charged. So the positive charges are coming from the protons that were already there before you strip the electron. So it's not excess. So truly, the only excess charge resides on the negative plate. That will always be the case. And so how much negative charge is there? Well, it's whatever the total charge of the plate is, negative Q. Taking the absolute value is just Q. So that's why the total charge on a capacitor is always just Q, because only one plate is actually charged with excess charge, and excess charge is what counts as it's only excess charge that counts toward the charge of a capacitor. So series, let's look at a series circuit, capacitors in series. Get this out. Series connection. Well, a series connection just means one right behind one another. Really what it means is the same current. We know current will ultimately stop, but while the current is flowing, the same current will flow through all of these. That's actually what it means, because it's on the same leg. So think of it, positive here, current goes in, and this is in one instant of time, because we know over time, as the charge, that's the other thing I didn't say over here, that when the voltage is a maximum, the current is going to die down to zero. And I implied it, right? Because as these, and I'm going to just go to with the conventional language, even though I've already explained to you what happens. As the holes are being deposited on the plate, it's harder and harder to deposit holes there. So once the voltage is equal and opposite the battery, you cannot push any hole onto the more holes onto the capacitor. But the capacitor cannot also push current back in the opposite direction or opposite orientation, because it's equal, because the battery has the same strength. So the current starts at a maximum and then dies down to zero as the charge on the capacitor starts at zero and then charges up to a maximum. They have opposite, change with the current versus the charge on the capacitor. So in any instant in time, it has the same current will be present on capacitor 1, capacitor 2, and therefore charge 1 and charge 2. So although we can talk about Q1 and Q2, and then a delta V2 and a delta V1, and also an E1 and E2. So we label them like that. So when we try to find, a equation, essentially what we're doing is, if I'm finding an equivalent equation or equivalent voltage. In other words, if I were to take these two capacitors out of the circuit and replace them with that guy, which we will call an equivalent capacitance, what is the relationship between the equivalent capacitor and the capacitance 1 and 2? That's what we're doing when we're finding these equations. It's just an equivalent relationship. So we replace it with one capacitor that I'll call CEQ for equivalent capacitance, such that the circuit would behave the same way. So if I take out C1 and C2, replace it with an equivalent capacitance, which just brings it back to being the original picture that we used, how does the equivalent capacitance relate to the capacitance on the individual capacitors? And I guess I should actually make this C1 and C2. And they would have Q1 and Q2 associated with them, which we know is related by that formula. So let's go through and do it real quick. So as I just told you, the place that is the start is with charge, because as the things charge up, and think about it like this, based on the argument I made over there. Maybe this is a better way to see it, or to think about it. As I pull off a positive, as I either deposit a hole, if you want to think about it like that, or pull off a negative charge, this thing is going to become positively charged. In that same instant, because it happens almost instantaneously, a negative charge is deposited over here. But a field begins to bring up here, or you could actually think of it this way. Simultaneously, when the electron is pulled off here, it's also pulled off this plate. So the electron is pulled here, so when that becomes positive, this becomes positive, and the charge is deposited over here, but then that charge is deposited over here. That electron is deposited here on that side. So they charge up pretty much simultaneously. And so we start to see the voltages created simultaneously. Now, they're not necessarily going to be the same voltage. They only will be the same if the capacitance are chosen to be the same. If the capacitance are different, then the ratio of charge to voltage is different. So the voltage is different. And well, the E fields in there will be different as well. But they charge up. But what is the same, even though the charge, even if I choose the capacitance is different, the voltage is different, the E is different, literally I'm pulling one charge off and putting, like, it's happening simultaneously. So no matter how I choose the capacitance and the voltages, the charges, the relative charges on the capacitors will always be the same. So when they charge up, if they're in series, they're going to have the same charge on them for the reasons I just mentioned. So even though I can define a C1 and a C2 and a delta V2 and a delta V1, I can start this discussion by saying at any given time, Q1 equals Q2 just equals Q. And therefore, ultimately, would just be the total charge would be the same. So that, and this, I make this an equation, and and also that's going to be the same charge on the equivalent capacitor. So we can say that as well. So it's just Q, which is also equal to Q equivalent. Because why is that the same? Because I told you that we're replacing these two capacitors with a capacitor such that all the properties of the circuit will be the same. So this then would have the be such that this equivalent capacitance would be such that the charge on the capacitor in any given time, like if I were to close these circuits simultaneously, then the charge on the capacitors would be equal to the charge on this guy. And it's confusing, right? Because you want to say that Q1 plus Q2 is going to be equal to Q. No, that's not the case, because then if this has 2Q and this has Q, then this is the capacitor that's causing the properties of the circuit to be different. So it just has Q. It's a little bit counterintuitive, but that is the argument. And that's what happened. That's how an experiment shows it to be an appropriate way to think about it. So what I say is that charge on capacitors in series is the same and is inherently the same, and it is the same as the charge on the equivalent capacitor. Charge on capacitors in series is the same. And is the same as that on the equivalent capacitor. On the or of the. All right. Okay, well, the other two things are obvious. The voltage on the capacitors are going to be different based on this relationship. Even though the charge is the same, if the capacitors are different, then the voltage has to be different in order to get the same charge. So we can say that the voltage, now, voltage is inherently different, and how does that relate to the equivalent voltage? Well, if I take a voltmeter and I put it across here, it's got to be the same voltage as this. So just logically speaking, that means that the voltage across this is going to be the voltage does add. It's going to be the voltage of this because it's a potential hill, right? So these voltage add, and they must be equal to the voltage across the equivalent voltage here for the equivalent capacitor, right? It's the delta V. So voltage on capacitors in series add to the equivalent voltage across the leg of the circuit. Voltage is inherently different. Now, it will be the same voltage if you choose a capacitor to be the same, but inherently different. So voltage is inherently
That's the word that I like to use. Different for series capacitors. And it leads to this equation that delta V equivalent is equal to delta V1 plus delta V2. There you go. Okay. And so finally, we can then use these two relationships along with this definition to come up with an equation for equivalent capacitance. So why don't I do that right here? Yeah, I guess I can do it here. So remember from this, we get that delta V is equal to Q over C. So I put this in here. What we have is, let's erase this now. What we have is delta V equal to Q over C. So what we're going to have is delta V equivalent is going to be Q equivalent over C equivalent is equal to Q1 over C1 plus Q2 over C2. Now, using this equation, I see that all the charges are the same. So I can say that, well, that's just Q over CEQ equals Q over C1 plus Q over C2. All the Q's cancel. And I basically have, for this example where I just had two capacitors, I get the result that 1 over CEQ equals 1 over C1 plus 1 over C2. But in general, I could have, several n number of capacitors. So in general, you could say that 1 over CEQ is equal to the summation of I equals 1 to n of 1 over the CIs. But I like to write it this way. I like to write it that CEQ is equal to the reciprocal of that quantity, I equals 1 to n of 1 over the I and the reciprocal of that. So, is that right? Did I do that right? Is this definition right? Something doesn't feel right. Yeah, that's right. C is equal to Q over delta V. So delta V is equal to, yeah. So basically, capacitors in series add reciprocally, right? Right. Series combination. 3, 4. Yeah, series combination. There's 3. Yeah, that's right. So capacitors in series add reciprocal. So, well, yeah. Well, I guess technically the reciprocal from this equation, the reciprocal capacitance adds reciprocally. So what we would say is that if we take the inverse of that, then the capacitance is the reciprocal of the sum of the reciprocals. Kind of confusing, but that is what it is. So what we could say is that the capacitance of capacitors in, or the equivalent capacitance, the equivalent capacitance of capacitors in series is the reciprocal of the sum of the reciprocals. Okay? The reciprocal is the equivalent the equivalent capacitance in series is the reciprocal series circuits. Just read this up. The equivalent capacitance for capacitors in series is the reciprocal of the sum of the reciprocals. So somewhere along the line, you can put that in for capacitors in series. And that's this equation right here. You know what? Time is moving. I got to take a little break for my next class. So that's one of them. I'm not going to, maybe it takes a little bit longer to do. So I'll let you do the, take a look at reading the parallel connection between now and Wednesday. And I will start the lecture on Wednesday by deriving the properties of capacitors in series, in parallel, that is. This was series. But just as a review, so there's three basic things I want you to remember from this derivation. For capacitors in series, charge is inherently the same and is the same for that of an equivalent capacitor. Voltage is inherently different, and the voltage adds. So I guess I could write a recurring relation, what's it called? Recursion relationship for this that looks something like this. It would be delta V is equal to the sum of the delta V's. So you can write a recursion relationship there for resistors in series. And finally, the recursion relationship for resistors and for capacitors. So I say resistors, I mean capacitors in series. The recursion relationship for capacitors in series is this for the capacitors, that the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. So yeah, you want to be able to summarize like that for the parallel capacitor connections as well. Okay. Well, that's it. I'll leave it today. Class dismissed.